third derivative of f at the point A. Right? Now from this equation, we see that C3 is equal to f triple prime at A over 3 times 2. Now, let me write one more. So that's 3 times 2 times 1. So what is that? That's f triple prime of A over 3 factorial. All right. Now, can you see a pattern here? All right. For C2, we have f double prime of A over 2 factorial. Right. Now for C3, f triple prime of A over 3 factorial. Right. So now we can guess. Right. What about C4? What about all the way to Cn?
F4 prime over 4 factorial.
Yes, exactly. Over n factorial, right? And on the top is f to the nth derivative, right? All right, so now let's, let me write it out. Okay. So now let's define the nth order Taylor polynomial for a function f. So this is called a Taylor polynomial. So let f be a function with f prime, f double prime, all the way to the nth derivative of f defined at some point A. So f is a random function, right? And the f prime all the way to the nth derivative of f exists at the point A. All right, so the nth order Taylor polynomial for f
Yes.
with its center at the point A. Denoted P sub n. Has the properties that it matches the function f in value, slope, and all derivatives up to the nth derivative at the point A. So that is P sub n of A is equal to f of A. P sub n prime of A is equal to f prime of A. And then all the way to the nth derivative. Right, so this this nth order Taylor polynomial denoted P sub n has these n+1 properties, right? So it matches this polynomial P sub n matches original function f in value, slope, and all the derivatives up to the nth derivative at this point A. All right? And that is our, this so-called nth order Taylor polynomial is our approximating function for the original function f. All right? So let's write this polynomial in sigma notation. So more compactly, so P sub n of x can be written as sigma k from 0 to n c sub k x minus a to the k power. All right, so where the coefficients c sub k are given by this formula. So it's the k, on the top is the k's order, the k's derivative of f evaluated at the point A, and on the bottom is the k's factorial. The k factorial. So for k equals 1, 0, 1, 2, all the positive, all the way to n. All right, so that's our Taylor polynomial, and you see that the linear polynomial and the quadratic polynomial we just derived before is just a special case of this nth order Taylor polynomial. Right? When n is equal to 1, that's the linear polynomial. When n is equal to 2, that's the quadratic polynomial. All right, so now let's look at example 1.2. Let's find the Taylor polynomials P1 all the way to P sub 5, centered at 0 for this function, for the sine function. All right. So you see that the Taylor polynomial has a certain form, right? So this is the exact form, right? So you see that in this definition, actually, it tells us how to find the Taylor polynomial, right? What we need to do is just find these coefficients, c sub k, right? K from 1 to whatever the order of the Taylor polynomial we're looking for, all right? So here, that's the formula for the coefficients, and for the rest of the of that polynomial P sub n, we just that's fixed, all right? So now here, first let's find the P sub 1 for this sine function. All right, so in order to find the P sub 1, so what do we need? So P sub 1 of x is equal to sine of 0, right? So we're looking for the polynomial, Taylor polynomial, first order Taylor polynomial, centered at 0, right? So for the constant term of this polynomial, that's simply the original function evaluated at the center, which is 0, right? And then what? Plus sine prime, and then at 0, x minus a. Oh, sorry, x minus 0. Right, so we're exactly following the definition here, right? Now, that's simple, right? The derivative of sine is cosine. Cosine 0 is equal to what? 1. It's 1, so it's x. So P1 is equal to x. Very simple, right? Now what about P2? So P2 is built on P1, right? So simply add one more term to P1. So P1 is equal to x Now, we add another term to P1, which is,
What happened to the sign of zero?
what happened to, what?
The sign of zero at the beginning.
Zero. Sine 0 is u 0.
That's right.
Exactly, that's 0. Yeah, x is
Okay.
from here. X is from here. So
All right.
That's 0. Yeah, you're right. So, okay, so now here, for P2, we need to have this. We need to find the second derivative of sine function and then evaluate that at 0. By the way, why do we evaluate this at 0? Because that's the center, right? So it's important, right? So to write a Taylor polynomial, we need to know two things. One thing, what is the function f, of course, right? What is the function f? And second thing, what is the center of this Taylor polynomial, right? Because we need to evaluate this at the center, which is 0, and then divide by 2. Or you can write 2 factorial, the same thing, right? And then x minus 0 squared. That's P2. But what is the second derivative of sine function? So first derivative cosine function, second derivative is negative sine function at 0, which is 0, right? So that's 0. So 0 times anything is equal to 0. So P2 is equal to P1, right? So in this particular example, right, so P2 is not better than P1 in terms of the approximation, right? So what about P3? So P3 is going to be P2, sorry, it's going to be P2 plus one more term. P2 is equal to x, and we add an additional term. And by the way, the general formula for the additional term is going to be the third, compare the index. So the third derivative of sine function at 0 over 3 factorial times x minus 0 cubed. All right, so now only thing we need to do is, what is this? So sine, cosine, negative sine, negative cosine, negative cosine, right? So negative cosine and 0, negative 1. So that's equal, okay. Minus 1 to the 3 factorial x cubed. So far so good. All right, so now what about the force? So the piece of 4 is going to be piece of 3, and then plus one more term. And that term is going to be the force derivative of sine function at 0 over 4 factorial times x minus 0 to the 4th power. So what is the sine? The force derivative of sine? 0. Okay, it's sine. Okay, it's either positive or negative sine function, right? So you see this sine function, the derivative of sine functions, right? So you started off on sine function and then cosine, sine, cosine, sine, right? I mean, forget about the plus or minus in the front, but it's sine, cosine, right? So for the even numbers here, so that's going to be some plus or minus sine function, right? And that's evaluated 0, always 0. So that's equal, P4 is equal to P3. The last one, P5. Okay, so P5. I will write this out for you. All right, so it's going to be 1 over x, 1 over 5 factorial times x to the 5th power. All right. So yeah, it's the same thing. We're just repeating the same thing. All right. So now this is the idea, right? So that's the 5th order Taylor polynomial for the sine function. Center at 0. All right. So now if we use a different center, that's going to be a whole different set of Taylor polynomials, right? So the center is important. Okay. So now we can find like whatever the order of this Taylor polynomial for this function f, for this in this particular example for the function sine of x. And then we can use this to approximate the sine function. Near the point 0, that's important, right? Right? It's important. The x has to be really close to 0 to have a good approximation, because what we're talking about is all about the area around this center point, 0 in this particular example. All right, so now the next natural thing to ask is how good are these approximations, right? So let's say we can always use a straight line, right, or linear approximation, or we can use a quadratic approximation, right? We got a sense, right? The higher order Taylor polynomials will give us better approximations for the original function, right? But we still need to be precise. So how good are the approximations? Right? So now we're going to define a new term, which is called the remainder for the Taylor polynomial. And the remainder is simply just the difference between this polynomial function and the original function, right? So that's the remainder. So the definition. So let P sub n be the Taylor polynomial of order n for f. So the remainder and using P sub n to approximate f at the point x is simply the difference between this original function f at this point x and the polynomial P sub n at this point x. Okay, so another word for this is simply just the error. The error for this approximation, right? So we want to use this P sub n to approximate this function f, right? So now, at some point x, right, so near the center, all right, so in this definition, we didn't identify what is the center for this P sub n, but that's okay, all right? So as long as x is very close to the center, all right, so we can use this approximation, and then we can talk about the remainder, which is simply the difference between the true value and this approximation. Okay? So it will be really nice if we can find a boundary, if we can find a bound for this this error or this remainder, right? So then we can say, all right, so so what degree of Taylor polynomial do we need to get a really good approximation for this function f? All right, so now we have to define what is a good approximation, right? We can define what is the error, right? So what error, I mean, can you, are you okay with, all right? So once we decide what is the error, right? So then we can say, all right, so can we find a higher polynomial, can we find a minimum n so that the P sub n and the difference between P sub n and f is really small, smaller than our prescribed error in the beginning, all right? So that's the idea. All right, so now it's really nice, right? We can use the mean value theorem from Cal 1 to get a very explicit formula for this remainder. I mean, right now this remainder seems like from the definition, this remainder looks very abstract, right? It's the difference between this and this, all right? So that's very abstract. Okay, so using the mean value theorem, we can find a formula for the remainder, all right? So here, we have a theorem So that's called a Taylor theorem. Okay, so let f have continuous derivatives. Up to f n plus 1 derivative. On an open interval. I. Open interval I containing the center point A. Now for all x in this interval I, so f of x is equal to p sub n of x plus r sub n of x. So this is obvious, right? This is obvious. By the definition of this remainder, we know, right? So we're using this p sub n to approximate this f. But okay, without this, we can only say this is approximately equal to that, right? Without this. Now, that's why we have this remainder, right? So the remainder is simply the difference between this. So with the remainder, we can have an equality here, all right? And where p sub n is the nth order Taylor polynomial. For f centered at A. Okay, the remarkable thing about this theorem is we can find a formula for this remainder. So the remainder is the n plus 1 derivative of this original function f evaluated at some point c. And I will tell you what is this c. So c is a number over n plus 1 factorial times x minus a times n plus 1. So by the way, so you see the remainder is a function, right? It's a function. And this function is given by this formula. Right, so for some c, some point c, between x and a. Right, so c is a number. C is a number between x and a. So this is a r sub n. So let's look at this formula for r sub n, right? So the remainder, right? So let's look at this. What does this one look like? By the way, so first let me write out the last term of this nth order Taylor polynomial for f centered at a. So what is this p sub n? P sub n here is f of a. The first term is f of a. Now what is the last term for p sub n? It's nth order Taylor polynomial. So that's going to be the nth derivative of f, right, evaluated at the center A over n factorial, right, plus times x minus a to the nth power. That's the Taylor polynomial, nth order Taylor polynomial. Now let's look at the remainder. Seems like the remainder is simply the next term of this Taylor polynomial, right? That's the next term of this for this Taylor polynomial. I mean, which is the last term for the piece of n plus 1's order Taylor polynomial, right? Does that look like? Yes. It's very close. The only difference is here, right? So for a Taylor polynomial, look at all the terms. So the derivative of whatever degrees of the derivative evaluated at the center A, but this C is not A, right? C is it could be A, but it's anywhere between X and A, right? By the way, we still don't know where's X, right? X is a variable, right? X could be on the left of A, or it could be on the right of A. So anyway, so C is just a number between X and A, right? So that's the only thing, right? So this one just looked like the next term for this Taylor polynomial, all right? But the only thing, the only difference is here, all right? So it's evaluated at this point C, right? So C is a number between X and A. All right, so now we got a very nice formula for this remainder. All right, so now the goal, like I said before, the goal is, can we find a bound for this error or for this remainder? Because if we can find a bound for this remainder, then we can say, okay, how good is our approximation? Assuming like we're using the nth order Taylor polynomial, right, to approximate this function f, and then using this formula, we can say, okay, our the error is going to be anything, it's going to be something related to this function, right? So we can look at some examples. Let's look at example 1.3. So let's find a bound for the magnitude of the remainder for the Taylor polynomial of this cosine function centered at 0. So in this example, it doesn't identify what order Taylor polynomial, right? So we just assume as the general nth order Taylor polynomial. Right? We're going to use the nth order Taylor polynomial to approximate this cosine function. And our goal is, let's find a bound for this remainder, right? Which means let's find a bound for the errors. Right? So let's write out the remainder. So what is the remainder for this approximation? So it's f to the n plus 1's. Okay, so it's a cosine function. So it's a cosine to the n plus 1 derivative evaluated at some point C. All right, so now you see the tricky thing is here, right? What is C? Right? We don't know what is C. Right? So we just know C is between X and A. Right? But let's think about this. Okay, it's cosine of the n plus first derivative of the cosine function evaluated at some number C. And on the bottom is n plus 1 factorial. And then what's x minus 0 to the n plus 1. Now we want to find a bound for the magnitude of this remainder, right? So the magnitude, which means we just take the absolute value of this. All right, so now let's look at the absolute value of this remainder. All right, absolute value here. All right, so let's look at this. First, let's look at this one. Cosine n plus first derivative of cosine function. What is that? So what's the derivative of cosine function? Sine, negative sine, right? And then the derivative of that is negative cosine, and then sine. You see, it's just like before, right? It's either sine or cosine, depending on this n, right? But since we're taking the absolute value, we don't need to worry about the plus or minus, right? So it's either cosine or sine function here, right? And then evaluate it at some point c. Now, what do we know about this trigonometry function sine or cosine function? Are they bounded? Yes. We can say, all right, so this part, all right, so let me write here. So this part is always bounded by what? It's always bounded by 1, right? It's always bounded by 1. And then this is x to the n plus 1 over n plus 1 by 1. So I didn't put an absolute value here because n plus 1 factorial always positive. Right? Okay, so this is always bounded by 1. Actually, this is always smaller than or equal to 1, right? This one. Okay, so now we got an inequality. And that's a very good inequality. That's 1 over n plus 1 factorial, and x to that. All right, that's it. That's a bound for the magnitude of this remainder, right? Now you see, the whole process, the only tricky thing is how do we deal with this? How do we deal with this, right? And C is something that we don't know, right? So we just know C is between x and a, but still, it could be anywhere between x and a, including x and a, right? So the tricky part is how do we deal with this, all right? So we have to use some previous knowledge to deal with this. Like here, we know that the sine function or cosine function is always bounded by, the absolute value is always bounded by 1, right? So that's how we get rid of this, right? Now we got a bound. But people will say, okay, what about this x here? And what about this n here? By the way, so, right? So n is the order of the Taylor polynomial, right? So that's how we make the error smaller, right? You see from this, you see that if we increase n, right? If we increase n, so what do we got here? The denominator is going to be bigger, right? Now, if we increase n, okay, it seems like we got a higher power for this absolute value of x. But remember, what is the center of this Taylor polynomial? 0. And we're assuming that x is really close to 0, which means x is smaller than 1, right? You raise a number smaller than 1 to some power, high power, that will only make it even smaller, right? So that means if we increase n, the magnitude of the remainder will be smaller, right? So which means we're gonna get a better approximation using the Taylor polynomial, right? So that's the idea. Let me write down the theorem. Okay, so write down the theorem. Okay, so estimate of the remainder. So let n be fixed. Oh, sign your names before you go. Sorry, I forgot that. Fixed positive integer. So suppose there exists a number m. So capital M is just a constant such that n plus 1 derivative of f evaluated as c is less than or equal to n.